Today on The Future of Everything, the future of photonics. Photonics is the science of light, photons, the particles of light, how they are generated, detected, manipulated. Light is critical in fiber optics. They allow very fast connections between computers. The ones and the zeros that they encode often through pulses of light, the digital signals, transmit internet, television, phone, and even can be used inside computers to transmit information. It can be pulses of light or it can be more complex. Now, amazingly, fiber optical connections, which are basically these long pieces of very, very pure glass, can move an optical signal very fast and pretty far, and even in bended pathways. But they have to be amplified eventually in order to keep the signal strong. Light travels very fast, around 886,000 miles per second. And although it's fast, it can still sometimes limit communications. It's not just an issue of how fast the beginning of the signal gets there. It's an issue of getting the whole package of information to the receiver so that you can watch your movie, read your email, listen to your song, and of course, other important things. So you want to get there quickly and you want the whole package to be delivered. Dr. David Miller is a professor of electrical engineering and applied physics at Stanford University. Before coming to Stanford, he worked at AT&T Bell Labs. His work focuses on optoelectronics, optics and information sensing, interconnects, and the processing of signals. David, we hear that silicon computers are starting to reach some fundamental limits. You're working on these optical technologies. Are they also hitting up against limits, or is there a lot of space to grow?
Hi, Russ. Yeah, there's a tremendous amount of space to grow in optics. That's one of the fantastic things. It's one of the few places where there's sort of orders of magnitude of headroom left, as I would talk about it. So the transistors we've been working with for a long time, Moore's law, which many people have heard of, has been this exponential growth in electronics. That has really sort of stopped. It's not that we're not still making some progress, but it's really hit some pretty difficult limits.
And as I understand it, it's been on an exponent and it's very hard, which is one of these curves that's just going to the roof.
That's
right. It's hard to maintain that ever for more than a certain amount of time.
Right. And, Moore's law had been on the go for, 50 years almost, but it has reached various kinds of limits. One is it's difficult to make the transistors much smaller, but a much worse limit has been emerging in electronics, which is the wires. The wires just cannot carry any more information. And chips are extremely constrained by that. And it's if you think of a silicon chip like something that's processing the information inside your computer or your cell phone or inside one of these gigantic data centers, it's kind of like Manhattan Island. There's dense collection, for example, of people on Manhattan Island.
Yes, there is.
You can't get things in and out. The roads are completely saturated. The roads are the equivalent here of the wires that I'm talking about. And there's really nothing left to do with the wires. We've pretty much maxed out the ability of wires to carry information. So the chips are really rather choked. They can do all this processing and they could even do a bit more, but they can't get the information in and out.
And we're talking, when you say wire, you're talking about copper through which electrons...
That's right. That's right. And if you look at the surface of a silicon chip, it's like a 6-level Manhattan Island. It's not just one level of roads. They built another level of roads above that and another level of roads. In fact, most of the fabricated volume in a silicon chip is actually wires. It's nearly all wires. I got some pictures once of Manhattan Island in about 1890 or something. And if you look at Manhattan Island in 1890, you find that the streets above the road surface are actually filled with telephone wires.
So it was a chip. It was basically a huge chip. It was a chip,
right. They filled with these telephone wires, but the wires have actually filled up all the space available. There's no more space for telephone wires. And what they then had to do was change the way that they sent signals over wires. And there was something they could do about that then. They went from very simple-minded signaling to stuff that could handle a lot more. And in fact, it was one of those pieces of technology that was licensed by AT&T at the time that made AT&T into the dominant long-distance carrier of information.
Yes. Okay, so now we have a problem. Where is optics? What is the potential for optics? Is it hitting up against the same limits, or do we see a clear field?
Yeah, the great thing about optics is we really see a clear field. mean, you and some others like me may be fortunate enough to have actual optical fiber into our homes. That fiber has the capability of carrying not 10 times more information, not 100, not 1,000, not 10,000, but possibly even 100,000 times more information than we are currently sending down it.
A single fiber.
A single fiber. And to give you a sense of scale here, if you had everybody in the world talking at once on the telephone, you could take that amount of data and get it all onto one optical fiber.
Okay, so that's amazing.
Yeah, that's the capacity of optical fiber to carry information. And that's just one optical channel. And when you and I are looking at one another with our lenses, and I think we both wear glasses here, we get yet more lenses, those lenses are capable of carrying millions and tens of millions of those channels, the equivalent of tens of millions of optical channels. So the capacity of optics to carry information is truly enormous. We're nowhere near the ceiling of that. Whereas with wires, we have really maxed out. On the chip, we are completely maxed out. There's nothing you can do about it. You can't solve the problem by making the chips all bigger or making the chips all smaller. It turns out to be what we call a scale invariant problem. We have really maxed out on our ability to send information on wires.
So it strikes me that this is the opportunity to kind of help decongest Manhattan and decongest these chips. Where is the science? Like, do we know that we can build devices out of light that traditionally had been done with electronics? It seems to me that there's a lot of fundamental questions about, can they do the same type of manipulations of information?
Right.
Can you miniaturize them? So where are we in terms of the basic science of whether or not you can replace these electronic type components with optical type components?
The main replacement we've been talking about up till recently, in fact, we can talk about that later, but the main replacement we've been talking about is for the communications. It's not the logic. We're not talking about making optical transistors. We do know how to do that, but it's very difficult to make them competitive with electronic transistors. Electronic transistors are fantastic.
They've just been highly optimized for 50 years.
That's right. And over the last 40 years or so, we got very, very good at sending information over optical fiber using light. And the components that you put on the end of that, there was no need to miniaturize those. There was no need to make them particularly low power. You could pay any amount of money for them because you were getting so much benefit.
Right.
So the traditional, as I could call it, optical technologies for working with fiber, they're a bit clunky, a bit big. They're very, very high performance, but they cost a lot and they took a lot of power. Now, in the laboratory, we have certainly made the devices that could do the job we need. For example, if you wanted to get the information on and off the chip, we have the devices that could do that. We demonstrated all those things. We understand the physics pretty well. And we have credible technological paths by which you could get those devices in together with the electronics.
Is it primarily a question of miniaturization, or is it much more than that?
You certainly need to miniaturize them, because if you don't miniaturize them, you don't get the energies down.
Right.
And incidentally, the whole issue of energy is another enormous one. We're currently at a situation where our handling of information takes maybe of the order of 10% of all electricity.
Yeah.
That's the scale we're at. And so you can see a problem right there, for example. If we wanted to keep on scaling up our use of information, we wanted to do 10 times more information. That sounds enormous, but that we go at least that much in a decade. Mm-hmm. Right? The growth of our use of information is at least a factor of 10 a decade. Well, if we didn't do something also about the energies, then we would use 100% of all electricity in a decade.
So the optical replacements that you're working on can't just be energy neutral. They have to start reducing energy requirements drastically.
Yes. And the good news is that in electrical wires, if you make a longer wire, basically you'd need to take a proportionate amount more energy to send the information down, at least on the scale inside machines. Right. So if I went from, a 10 centimeter wire to a 1 meter wire, it would actually take me 10 times more energy to send the information down that. Optics is not like that. Optics has very little increased energy to send the information a longer distance, especially on the scale inside, inside your room, inside a warehouse. It takes no more energy to send it over a long distance than over a short distance. So that's a big advantage of optics. It's a rather fundamental thing. It's actually a piece of quantum mechanics. It's what they call the photoelectric effect. We don't we're not sending voltages down optical fibers. We're sending photons. Now, that's one of the benefits of optics, but it still doesn't solve all the problem, because you need to make the devices on either end of those optical connections have very low energies themselves.
Right.
So that they don't take more energy to drive than it was taking you to send the information down
So
the
you were
wire.
describing them before, that in the long haul kind of telephone system, you had relatively big boxes receiving the photons and processing them. You can't spend all your energy on those, because that will then reduce the advantage of having the very efficient wire between them.
That's exactly right. Now, the good news there also is that we know how to make the devices, the optoelectronic devices, I would call them, the ones that go in and out between optics and electronics. We know how to make them have very low energy. And we're starting to figure out how to put those onto chips. Right. And the first place you would use them would be for going on and off the chip.
Yeah.
Maybe eventually you'd use them for going distances across the chip. But the benefit of optics gets larger and larger as you think about longer distances.
So I wanted to ask you about on the chip, because we've all seen these pictures, the microscopic pictures of the chips. And as you said, they look like Manhattan with all of these, I guess, etched wires on the silicon. Are we going to someday see chips where within those etchings are little fiber optics that are also kind of worming their way through on the chip?
We certainly are, and there is a good technology that is a technology base that we're now having, which you can get these things manufactured, which is what's called silicon photonics, where you actually reuse the technology we used to use and still use for making silicon electronic chips, and use it for making what we'd call photonic chips. Or even we can think about combining the two, having a combined photonic and electronic chip. And part of the key of that is that the materials that we use in silicon electronics, many of them, including silicon itself, are actually very nicely transparent for sending light.
Yeah, as I recall, there's silicon in glass.
Right. So the silicon and glass are two major materials that you use to make silicon integrated circuits. Now, glass is transparent, obviously, in the visible part of the spectrum, and also in where we end up sending the information, optical fibers. That's actually in the infrared part of the spectrum, be longer wavelengths than we can see. Silicon turns out to be transparent there. Silicon itself, if you look at it in ordinary daylight, is this kind of gray metallic-like looking material. But when you go out to the longer wavelengths where we use optical fibers, actually silicon itself is transparent. So you can use, rather usefully, silicon as kind of optical wiring.
That seems to be a godsend, because now so much of our technology is immediately repurposable.
That is exactly right. So that is happening. So this is now actually a growing industry called silicon photonics. Now, there's tremendous good news there that the silicon is a good optical material for sending light, but that's actually at the core of why it's not a good material for detecting and generating or modulating light. Silicon is not a good material for making those devices, at least in that part of the spectrum, that convert between optics and electronics.
Right, because it's basically such a good pipe that obviously a good pipe doesn't mess with the contents of its pipe.
Right, and silicon is good at detecting light in the visible. That's our cameras are all silicon, but it's not good in the infrared where we want to send all the information, especially over fibers. So we need some additions to the technology there. And we do know how to do that in the lab. And that's one of the challenges, is how to take that forward into generating a viable technology at a good cost.
So as you look at these challenges, and so you're looking at a world where, as I understand it, you're at least the first challenge is to get the interconnects between chips to be much more optical and much less copper wire. What are the main challenges that your group is looking at within that spectrum of problems? And I guess that's the question: is what's the hardest problem there?
The hardest problem has been historically getting the devices, especially the ones that would convert from electrical signals into optical signals, at a low enough energy. As I said, we cannot afford to spend a lot of energy to do this. If we do, the technology just isn't any use. But physically, we have figured out how to do that. And one of the tricks that we came up with is actually to incorporate some germanium together with the silicon. It turns out that germanium is actually quite a good material for some of the optical devices, the modulators that would turn light on and off. Germanium turns out to be very good for that. Germanium is the original material we use to make transistors. And there is already some germanium in silicon integrated circuits. It's used for a slightly strange purpose. Germanium atoms are bigger than silicon atoms. So if you put some germanium bits of germanium inside the silicon transistor actually stretches and compresses bits of the material that has a benefit for silicon transistors that actually makes them conduct better.
So it's a beneficial contaminant, basically.
It's a beneficial contaminant. The germanium is a beneficial contaminant, and we can use it for some of the optoelectronic purposes.
And so if I understand the challenge here, I'm on a wire, electronic copper wire, electrons are coming in, and you have to figure out how to build a device, maybe out of germanium and other things, that's going to take those incoming electrons and output photons.
That's right. Or at least I could send photons in, and then I have something that turns on and off the transmission of the photons.
So, or the opposite.
Shutter. Right. I need one or the other. I don't necessarily have to generate the light on the chip. That's a secondary issue. We can generate light off the chip, but we need to make a kind of controllable shutter that can turn it on and off.
Gotcha.
The good news is we have figured out how to make those kind of devices in the laboratory.
Okay, so one of the things you've written about, I want to ask, we have a couple minutes left in this segment, is optical information sensing. So can you define that for me and tell me why that's a critical part of this whole enterprise?
Yeah, so the optical information sensing is really another part of the whole information problem. But we do it all the time. As the cell phone cameras have completely transformed the world. Nearly all cameras are cell phone cameras. They're actually made out of silicon, as I said, and they're very good sensors for simple kind of sensing, for imaging, looking at pictures. But what if you want to do more than that? What if you want to understand more about what's going on inside the image? Can the optics help you with that? And as we've talked about, light coming at you has a tremendous amount of information, a truly astonishing amount of information. And we only process a small fraction of it when we form an image. There's lots more we could do with it than that. So for microscopy or for sending information through the atmosphere, for example, we would like to have systems that were more sophisticated, somewhat smarter. They could be, for example, adaptive systems that would look at just what we need out of a scene and stop overwhelming the rest of the information processing behind it that tries to interpret the scene. That's a major information processing problem, by the way, if you really try to interpret a scene.
Yes. Okay, so optical information sensing is this idea that you're building cameras that I'll call them cameras, but they have more narrow bandwidth in some sense, that they're looking at certain types of light or certain types of phenomenon and pulling that out from the mass of noise that's also present.
But they could directly extract features from the image.
Yes.
I could directly extract all the corners or the edges. That would be among the simpler kinds of things I could do. I could also imagine automatically locking on to certain things and tracking them, all in the optics.
Okay, so as a biologist, now you're starting to describe some of the early visual processing that happens in the eye. Right. And maybe we can build electronics to do similar early processing of images.
Yes, so the optics could do that. And optics can also do something that is difficult to describe. It can do something that you can't do just with a camera. So you look at this camera, you in your brain, you construct, I'm probably sitting here on a chair and I'm probably not just a two-dimensional image, but you can't actually tell that. Right. What you could be looking at here could just be me on a TV screen that the camera is looking at.
A deep fake. You could be a deep fake.
I could be a deep fake. People have often said that about me. I could be a deep fake. You couldn't tell the difference. But optically, we could tell the difference. Optically, we could directly perceive depth and things like that. We could tell apart the deep fake.
So that leads to a whole nother discussion, which we will get to in a moment. This is The Future of Everything. I'm Russ Altman. More with Dr. David Miller about the promises of photonics and optoelectronic connections next on Sirius XM. Welcome back to The Future of Everything. I'm Russ Altman. I'm speaking with Professor David Miller about optoelectronics. And in the last segment, we really beautifully set up why this is so important to move from copper to optics. I want to ask you, what are the challenges and the difficulties in making all of that happen? Because as an engineer, you have a theoretical solution, but I know that you don't rest there. You want to have an actual scalable, workable solution. So what are the difficulties?
One of the main difficulties is that the historical technology we have for long distance, as I said, makes kind of big clunky objects, but they work very well. But if you're going to work inside the machine, we need to make them very small, very low energy. And if we want to get them on chips, that's even more so. And that's where the technological challenges lie. But an important point to make is that we do have the devices. We can make them in the lab.
That seems critical because it means
Right.
it's not a question of whether it's possible, it's a question of
Right.
getting it to work.
We sorted out the physics, we sorted out the applied physics, we've made the proofs of principle in the lab, and we can also see the technological paths by which we could incorporate those.
Okay.
But that's a chunk of work, partly because you would probably have to add some materials to all of that magnificent silicon manufacturing process. And that's a very tough thing to do. It's not that you can't do it, but you have to sort out a whole lot of things when you try to add another material. It took tremendous investment in silicon chips just to substitute copper for aluminum in some of the wires. That was a major technological investment. And we were asking for other materials than that.
And there's a huge, I mean, this is obvious to say, but there's a huge national and international infrastructure for building things the way they're built now. And you're basically asking to repurpose that infrastructure for this entirely new endeavor.
Now, we can get somewhere with the technologies we have. It won't quite get to where we really want to be, and it won't quite open up all of that headroom of orders of magnitude unless we make some additional changes. But we could do it. So that's one of the technological things, but it would mean incorporating some new materials possibly into the process. And it also requires very, very close integration. The optical devices, they don't have to be on the scale of the transistors. Transistors are basically really, really tiny.
Yes.
Of order these days, the size scale is of order 10 nanometers, which is very, very tiny. Hundredth of a micron, and a micron.
Much smaller than a human cell. Much smaller.
Right. Much smaller than human cells. That's a micron scale object. This is like another 2 orders of magnitude, another factor of 100 smaller than that. Transistors are really small. The optical devices don't have to be that small, but they have to be on the micron scale. So that's, a small living cell, if I understand living cells at all.
Yes, that's exactly
You need to get to that kind of scale, or possibly a little smaller. But so it's not fundamentally a challenge to make things that small, because we can make things 100 times smaller than that. But we do have to get them very close to the electronics. And so that can all be done, but it's technological investment to bring it to scale. And we've sort of seen this coming for a while, but it's only recently that the crunch has really come in the electronic systems. They're really hurting.
They would buy this technology now if it was off the shelf.
Yes, they certainly would. And they're already starting to try to create it. There are length scales in these systems. Going between cities is hundreds of kilometers. Going under the seas, thousands of kilometers. We can do that in optical fiber. Inside the big warehouses and data centers and the like, we're talking about kilometer for the longer fibers. Between the big racks of equipment, which are like, they're the size of refrigerators, basically, there are lots and lots of refrigerator-sized objects inside the data centers. The connections between those are from meters to tens of meters to kilometers. And then inside that is when you really start to get very large numbers of connections. And once you get to those scales, then we need these newer technologies. And we can sort of progress inwards towards the chip. And that is what will happen if we don't do anything radical. We will see a progressive evolution towards shorter distances.
Yeah, so this is fascinating. So we've really nailed the kilometer level communications.
Yes.
And now you're talking about meters and centimeters. We may get to microns, but really the sweet spot is really at a scale where the human eye would see it.
Yes, that's right. That's exactly right.
But this would have a huge change in the speed of communications within the computers, and also the heat that they generated, as we discussed earlier.
The optics doesn't require an amount of energy that's proportional to distance, whereas electronic wires basically do at these shorter distances. And you're right. My vision is we try to get it down to the centimeter scale level. There's a tremendous benefit in doing that. And if you generate that technology, if you decide just to go across the chip itself, you just use the same technology.
Right.
So, there's a kind of big technology break if we get to the technology that's good enough to get right down to the centimeter scale. And in the lab, we could see how to do that. So there's tremendous headroom here, but yes, there's technological investment. But I'm more optimistic that that's going to take place because the crunch has really come in the electronic systems. They're massively constrained by wiring. And as we start to think about some of these other emerging areas like deep learning, artificial intelligence, and so on, they are even more demanding on all of this business.
Yes, so I wanted to ask you, because you've written intriguing papers where you've, I don't know if you've coined it, but you've definitely used the phrase deep optics, which sounds very, very buzzword compliant to me. What is deep optics, and why should we be excited about it?
Yes, deep optics is more exploratory. It's more speculative. It's the idea also that we might not just do the interconnects with optics, but we certainly want to do that. We might think about using optics for some of the processing again. So it's this idea, it's optical computers are things that people have looked at periodically over the last 40 to 50 years, but they've never worked out. The optical transistor doesn't really compete with the electronic transistor. But we start to see that there are ways we could use optics that are different, and partly because now we can make very complicated optical systems. Exactly those kind of optical integrated circuits we were talking about. We can get to pretty high complexities there. And one of the intellectual breakthroughs is we've started to understand how to control complicated optical systems and how to program them. We've made some intellectual advances in that. We could think of an analogy, a very difficult processing problem. I have 4 faucets or taps, and I turn them on and off. So I got 4 streams of water, and I put them into a pipe or over a bed of gravel or something, and I get this very mixed up thing at the far end. That is, first of all, that bed of gravel is actually doing some information processing. We may not know what it is, but it's actually is mixing these pipes of water, and these streams of water in very different ways. But we have understood now the optical equivalent of those classes of systems. And we can now make and program and actually self-program an optical system that could separate out the streams again at the end. So that you have four different streams, for example, coming in from 4 different faucets or taps you're turning on and off, going into this great long pipe or over a bed of gravel. And at the far end, we put this magical system that ends up separating out the 4 streams of water again, as if they were just coming out the faucets.
And that's proof, basically, that the bed of rocks that you sent these faucets through did not purely randomize those 4. There must have been a conservation of that information. And therefore, if you can specify, tell me if I'm right, if you can specify what's going into that bed of rocks, and if you can specify what that bed of rocks at a very fine detail is doing to each of those streams, you could then design beds of rocks, if I'm going to continue that do things that you want them to do.
That's exactly right. So we could make the optical equivalent that would separate out the bed of rocks processing, which means we could make the bed of rocks processing because it's just the same thing flipped around. So we know how to do that, and we know how to program that, and we know how to self-configure that. That is, as an automatic way, we could actually separate out the streams of water again at the end. We actually know how to do that now, and those have been major intellectual advances. So not only can we make very complicated optical things, we also know how to program them and even have them stabilize themselves and even configure themselves. That's a major intellectual advance, and there's nothing like it before in optics.
And it's a great thing for us to end on, because this is where it's not just the interconnects, but you go into a computer and the actual computation gets done with the photons.
That's right. We take advantage of all the things the photons can do. It's very exciting.
Thank you for listening to The Future of Everything. I'm Russ Altman. If you missed any of this episode, listen anytime on demand with the SiriusXM app.